Hello and welcome back, my forest-dwelling physics friends. All right, so we're looking at a projectile motion equation or sort of problem right here. And here's the question. If I chuck a rock at 7 meters per second, 53 degrees is the angle, and it goes over a cliff and has another 50 feet to fall, how fast is it going to hit the ground? So what's going to happen is when I chuck something at an angle, right, I'm going to have a vertical direction and a horizontal one, right? And so that horizontal direction isn't going to be affected by anything. So let's say there's no air resistance here. Air resistance might affect it slightly. But the velocity in the x direction is just going to keep going until it stops. So whatever the velocity in the x direction initially is going to be the same as it is over here. But the vertical direction is going to go up and then come down, and it's going to have the same velocity here as it does right here. Right? It's going to go up to 0 and then end up right back in the same spot it started right here. But then we've got another 50 feet to fall. And so our vertical is going to increase speed. So my velocity, of course, then is going to increase right here. And so it's going to be a lot more than 7 meters per second. So how do we do this? Well, let's go ahead and just resolve these vectors to begin with, just to find out what I have right here, because that's a pretty easy one. So you could see here that you could take the sine of the angle theta here, which is 53, and that is going to equal this opposite, and this is our velocity in the y direction. Remember, this is our velocity in the x direction. So that's going to equal our velocity in the x direction, which is our opposite, divided by our hypotenuse, divided by 7. So if I multiply 7 by the sine of 53, I'm going to get 5.59 meters per second. Okay, so that gives me the velocity in the y direction. Now let's look at the velocity in the x direction. Well, that's going to be the cosine of 53. Right? So the cosine of 53, the cosine of the angle theta equals the adjacent over the hypotenuse. So this is going to be the adjacent over 7.0. So that one's going to be 4.21 meters per second. Now, we know since the horizontal velocity is not affected by anything, that's what this vector is going to be right here. So we have this 4.21. So we've got one part of our triangle down here. Now we know this distance is 50 meters, okay? So what we know is that that rock, starting from 0 here, going all the way down from 50, is going to, because of the acceleration of gravity, is going to pick up a whole bunch of vertical velocity. So what we can do is we can go back and use this old equation right here, right? So we have a distance final. So let's go ahead and plug that in. Our distance final is 50, right? And our distance initial, we want to start from 0 here. Plus, we want to start with an initial velocity of 0, because all we want to know is what is the total velocity that gravity does or gives the rock while it is traveling for 50 feet, and that's straight down. So our initial velocity is going to be 0, which multiplied by time final, of course, cancels that out. So all this is canceled out. And that's going to equal 1/2 times 9.8 times time final squared. So you can see right here that we have enough information to figure out the total time it's going to take for the rock to fall 50 meters. And from that time, we'll be able to figure out a lot of stuff. All right, so let's go ahead and do this. So 50 divided by 2 here. And then, or no, multiplied by 2, and then times 9.8. Let's see, what do we get? And then take the square root of that, and we should get 36 point, let's see, that may be the wrong answer. All right, here we are. So, we should get 3.19, I'm sorry. So 3.19 seconds. So if I go ahead and I solve this out, so what I'm going to do is multiply this by 2, so I end up with 100, and then I'm going to divide it by 9.8, and then take the square root of that, right? So a little bit sloppy math right there, but hopefully you understand how to solve for this time. So my time here equals 3.19 seconds. All right, so what am I going to do with that? Well, my velocity in the y direction, remember I started with 5.59 because that's what the rock has at this point right here. So it's got a velocity vector already of 5.59, right? Seconds. And I'm going to fall for meters per second. I'm going to fall for 3.19 seconds, and I'm going to then be adding to that the acceleration of gravity. So what I could say is my total velocity in the y direction is going to equal 5.59 meters per second plus 9.8 meters per second squared, because that's the acceleration of gravity, times 3.19 seconds. Because for 3.19 seconds, I'm going to be adding velocity to this initial velocity. And if I calculate that all out, I get, what do I get? 36.862, something like that. So 36.862 meters per second. So that's my velocity vector here in the y direction. So 36.862 meters per second. Okay, so now look, I have my y direction and my x direction. So to figure this out, all I need to do is the Pythagorean theorem. So I'll just kind of put that right here. Let me get a different color just so it's easier to sort of separate out what I'm doing. So my velocity final, and that's what I want to know right here. My velocity final vector is going to equal 36.862 squared plus 4.21 squared. So this should be squared too. Plus 4.21 squared. And if I take those, square those, add them together, and take the square root of them, I get my velocity final in here as 37.2 meters per second. So that's my answer right there. So this rock is going to be going 37.2 meters per second when it hits the ground. Now that's not good enough because it's a velocity vector. You also have to be able to find the angle. And so let's take a look at this angle right here. All right, to solve for this angle, I'm going to use the TOA, the TOA. And so I'm going to say the tangent of that angle is going to equal my opposite divided by my adjacent. So here's my opposite. So I've got 36.862 divided by 4.21, right? And so divide that out, and then in order to get the angle by itself, I'll take the inverse tangent of that. And what do I get? I get that my angle equals 83.5 degrees. So I need to add this on here. So I got this is a velocity vector. It's hitting the ground at a velocity of 37.2 meters per second and an angle from horizontal of 83.5 degrees. So hopefully that helps kind of show you, just kind of a more complex example of some of the kinds of things you can do with projectile motion. And one thing that we get out of this, we might as well just throw out here, any time you want to find distance in the y direction, right? Go ahead and erase some of this. So that's what we did right here. We took this and we turned it in. Distance in the y direction, a lot of times you have you don't have an initial distance and you don't have an initial velocity. So you could say, if that's the case, your distance in the y direction is going to be 1/2 acceleration of gravity, which is g times time squared. So this is kind of a new equation you can add into the grab bag here. All right, so I hope that helps, and we'll do more like that to come.